Hello everyone, welcome to this lecture series of engineering mechanics in which we are discussing about the dynamics aspect of the mechanics. We have already gone through the energy methods in which we have discussed kinetic and potential energy methods and how to solve the dynamics problems using these methods. Today we'll be discussing another alternative method of impulsive impulse momentum equation. This is also one kind of an energy method in which one energy is transferred to another system. So this is a certain kind of an equation which is used to model the initial position of the body and the final position of the body. So whatever the field variables are that needs to be obtained are actually derived using these equations. Now, first of all, before going towards that, we would like to discuss what is a impulsive motion or impulse force. So, as you can see here, any kind of a thrust occurring due to any injectable systems like this is kind of a rocket that actually provides a thrust, and it actually the thrust or the dynamo actually helps to make this rocket in a momentum further, and this kind of a momentum is a linear momentum. It is a linear momentum because it follows a simple linear path. In another equation, in another figure, you can see this is a wall and this is a certain kind of a train, and these are actually the test conducted. Impact tests are conducted, or crash tests in fact are conducted, so that the mechanism and the operating capacity of the trains are magnified, and they are actually tested. What happens if something happens in a real scenario? So in that also, a high velocity moving train actually got impacted towards this kind of a very similar to a rigid wall, and it actually crashes. So these engineers actually see how much is the amount of crash happens if something like this happens. So actually we were discussing about the impulsive motion, and the impulsive motion is in simple terms. uh, you can understand it in this way, like for example, if you have a football and you would like to kick this football, and after kicking it, it actually moves towards some another position too. So let's say this is position 1 and this is position 2. What you did not apply a force, you apply an impulsive force. You actually kick this football and gave this football a force. You did give this football a force, but the amount of force that is applied on this football was not very high, but it actually has a very limited time interval. So on the time interval at which it is applied is very small. In fact, it is delta t. So where delta t is very small, and the velocity with which it is moving is, let's say, mv1. So your leg is moving with the velocity of velocity of v1, and this is the momentum mv1. So you actually put a momentum here, and the force with which it is applied is called as a impulsive force, and we used to say impulsive force as F delta T is the impulsive force applied here. And due to the impulsive force and the momentum, this football actually changes its position from point or location 1 to location 2. So at this location 2 we will be having another momentum mv2. So this equation actually moves like this: mv1, the mass of the this football does not change actually. So okay, so it has an initial momentum of mv1, and then a force, a very uh, a force is applied on this football which is applied at a very short period of time. Okay, so impulsive force is any force that is applied on a very short period of time. That is a impulse or a thrust force, and it actually moves the body from location 1 to location 2, and at location 2 it has a new momentum which has same mass of the football in this case and new velocity v2. So the principle says that, like for example, this is the principle is actually derived from Newton's second law of motion, and this is F equals to ma, where a is the acceleration, so dv by dt is the acceleration, m is constant, we have taken it in the bracket, and this becomes a momentum, in fact a linear momentum. We can transfer dt here and we can try to integrate it within a time interval of t1 to t2. And it is very important to see that this time interval is very short in time, so this becomes a impulsive motion or impulsive force. Okay, and you can transfer this mv1 to here to make it in a formulated equation, which is written or read it like this: mv1 is the initial momentum of the body plus the impulse force applied on this. And what is the impulse force? Is this time t1 to t2, which is a very short time, and this is the force which is applied. And remember that this force is actually is the is the is the force applied due to the kick you actually offer to this football. So this is the force applied due to this kick. The only thing in this case of momentum is that, in this case of impulse, is that this force is applied on a very short period of time. So as a vector momentum, you can say that this is the initial momentum of this body or of this football plus the impulsive force that is applied on this body, which um, um, actually moves this football to certain direction. So we can actually add up to these two vectors and make a new vector mv2. So it can be added vectorially also. Okay, now you know what is a impulsive force or impulse momentum equation. So this is a very simple, it has a units of Newton seconds or kg meter per second square times seconds, which can be written as kg meter per second. As I said, as I've already defined, force acting on a body with a very short period of time, and that actually has a large enough to cause a significant change in the momentum of the body. This type of force is an impulsive force. So this is the impulse momentum equation: mv1 initial momentum plus any forces that is actually acts on the body for a very short period of time. There may be multiple forces also, equals to mv2, the final momentum of the body. This is an example of a baseball. So a baseball is actually this is where the bat of the baseball is. Okay, and this baseball or a bowler is actually throwing the baseball to the batsman. So so this is the direction of the momentum mv1. This is the direction opposed to this. Once it reaches to the batsman, it actually batsman used to hit this ball. So there are two components. One is F delta T, which is the impulse force actually hit by the bat, and one is the weight of the ball itself. But the weight of the ball is very small compared to this impulse force, almost negligible. Okay, we can consider that as zero. And combining these two, we have a new momentum of the ball. Once the batsman hits this ball, it has a new momentum mv2. So the momentum is actually gained by the this F delta T or the impulse force. Okay, and it can also change the sense of the ball also. As you can see, the sense of the ball or the direction of the ball was this was the direction, and due to the impulsive force, a high amount of force, the direction has actually changed. And some other non-impulsive force, as I've already described, WAT is some other non-impulsive forces which actually does not do any amount of work, or any amount of negligible amount of work, in fact. So this is the another problem which we have already solved. However, in this case, we will be interested in knowing the time required to stop the automobile. This problem we have already solved in the previous lecture in the examples of kinetic and potential energies. So this was the weight of the automobile, and this automobile is being driven towards the base. So, and this is an inclination of 5 degrees, and the automobile has having a speed of 60 miles per hour. And during this movement, there is a brakes are also applied. So we have already solved this problem. So a constant braking force of something around 1500 pounds. We have to determine the time required to stop the automobile. Now, what is trying to you are being given this problem so that you could also understand that there is no impulsive force in this problem. If you see this problem magnificently, so you won't find any impulsive force. Where does the impulsive force acts on this? Nowhere. No impulsive force is there. This automobile is actually having a inclination of 5 degrees, and it is moving down with a speed of 60 miles per hour. So it has a momentum, and v1 it has, and it is moving with the inclination of 5 degrees. So where does the impulsive force came? From nowhere. The impulsive force can only be assumed to come from the weight of this automobile, and not exactly from this weight of the automobile, because the weight of the automobile is very heavy and it is actually in the downward direction. But since it has an inclination of 5 degrees, so there will be a one component of this weight W, one component of this W which will be along this, and it is providing a small impulsive force to this car. Okay, so there will be one component which is the weight of the car, and that is only a component only. So let's see how the impulse momentum can be applied on this. So we have this force momentum um, equation, impulse momentum equation, and first of all we have drawn the FBD of this. So this was the initial condition, mv1 case. It has its velocity and mass. So this was the initial momentum plus, as I said, the weight times time required to move this vehicle from this location to this location. And there is a braking force also, which is trying to stop this or trying to decelerate this vehicle. So we have a weight of the vehicle and the normal force offered by the ground, and this Ft is the friction force or the braking force, and this also is multiplied with time. Okay, so time actually explicitly is included in the equation. So this was the initial condition. Only along this inclination we will be dealing with the components only along this inclination of 5 degrees. So this was mv1. So this is 4000 times, this is actually converted in the units, proper units. So this is actually this times w sine 5 degrees. So w sine 5 degrees, which component? This is this component moving in this direction, w times sine 45. So this will be a not will be a very huge component, will be a significantly small component, w sine 5 degrees times t, because this was the impulse equation and we are writing it in this form only, minus ft. This is the braking force, so minus ft. So this summation actually says that any impulsive force or component force minus any forces that are actually reducing it, like this braking force or any other forces. So we write all the forces within this bracket, any external forces, okay, times mv2. V2 is 0 because the vehicle has actually stopped. So this is 0. So this equation has been there, and we have explicitly derived for time t, which is actually came up to be 9.5 seconds. So one important thing to be taken from this problem is that the impulse force was not applied explicitly on this body. However, since this body has its own weight and that too large, so there will be, and it is traveling at an inclination of 5 degrees. If it would not have been traveling at an inclination of 5 degrees, the inclination would have been 0, then this sine theta would have been 0, and there will be no impulsive force. Then the impulsive force problem will not be there. However, since there is an inclination, so explicitly there was no impulsive force, but since the weight of the vehicle was there, so there was one component that actually acts as an impulsive force. So I hope this problem actually signifies that you can solve the same problem by using kinetic energy and potential energy methods, and can also solve this problem using this impulse momentum energy methods also. Let's see another problem, a good problem actually. And in this is a baseball, very certain example. A bowler has actually bowled this baseball to a batsman, and batsman actually hit this, and then once it has hit, so what happens after hitting it? It has given it an impulsive force at a certain point. Okay, at this point, at a very small interval of time, and due to this impulsive force, it actually changes its momentum, and it actually flies to some other place. So it has 4 O's of this is actually weight, 4 O's. Okay, it's a weight. Baseball, it's a US unit. They used to write it O's. Baseball is pitched with a velocity of 80 feet per second. So 80 feet per second is coming with this. Okay. After the ball is hit by the bat, it has a velocity of 120 feet per second. So remember that this is mv1. Mass of the this ball is 4 O's times v1 is 80 feet per second. Okay, and v2, mv2, and this is mv2, 120 feet per second in the direction shown. If the bat and the ball are in the contact for this much amount of time, so this will be having f delta t. Okay, so the contact time here is delta t, which is 0.015 seconds. Determine the impulsive force exerted on the ball during the impact. So the equation is already made. You have to just put in the values and obtain the impulsive force. But it's important that first of all you make a FBD or free body diagram, because this will be having certain components. We will be dealing this in terms of components. Okay. Uh, let's see this. One important point that I would like to mention, that we know that the direction of the impulsive force is this. Okay. This is the direction of impulsive force, F. But we do not use to deal it in certain directions. We used to deal it in x and y coordinate systems. So we'll be having a coordinate system x and coordinate system y. So we actually resolve this f in fx and fy, and after that we can add it and find it out the overall impulse force. Okay. So this was our problem. We have applied the impulse momentum equation, and now we will be having a free body diagram. So as we know that this is our xy system, mv1 is the momentum with which this ball is coming, plus the impact force, or the impulse force in fact, which has two component, fx delta t, fy delta t. Remember that the direction of the original, or the direction of the impulse force is this, but since we do not know this direction, we have broken down our impulse force in the x and y components. Okay, and this is equal to your final momentum of the. So we'll resolve the x components, all x component and all y components, and then we can further move. So this is minus mv1 minus, because this is the direction against the x, plus fx delta t, our only component along this, okay, is equal to mv2 cos 30 degrees. So cos 40 degrees will be this component, okay, and we have solved this for fx 89 pounds. In a similar way, we can solve for Fy also. So Fy, there is no Fy component here. So in terms of Fy, no momentum component in y direction, 0, plus Fy delta t, and then mv2 sine 40 degrees will be this component sine 40 degrees. Okay, solve for Fy. Once both of them are solved, we can write them in vector form like this. So this was the force equation, or force equation in vector forms, and this is in magnitude 97.5 pounds. And how it is obtained? Square root of 89 square plus 39.9 square. So you can find it out, the resultant. The resultant comes out to be 97.5 pounds. So this was a very simple problem. The important thing that needs to be taken away from this problem is that the impulsive force may not be given in the component forms. So overall impulse force will be given to you, and to obtain the overall impulse force, you can break down it in your defined or in your assumed component. Like in this case, we have assumed it in x and y directions, so we have broken down the components in these two directions. Okay, and another problem we can solve for another problem we have. Yes, we have another problem. It's a very interesting problem in which momentum transfer actually took place. And what happens in this? This is uh, a cart, and a package is dropped on this cart at a velocity of 3 meters per second. A package is dropped on this cart at a velocity of 3 meters per second. Now this cart is initially at rest and can roll freely on the ground. Find out the final velocity of the cart. That means after something, what is this? Actually, this is a package. So once this package is actually dropped on this cart, it can move freely along the horizontal direction. So once a momentum mv1 actually hits it, it actually moves to a certain position mv2. So where is the impulse force? We will find it out. The final velocity of the cart, impulse exerted by the cart on the package. First of all, the final velocity mv2, we have to find it out. This another thing, impulse exerted by the cart on the package. That means once this package actually hits this cart, what will be the impulse offered by this cart to this package? That means it is working on the Newton's third law of motion, action to reaction. And finally, the fraction of the energy lost in the impact. Remember that whenever an impact happens, there is some energy is always lost. So how much energy is that? So we'll find out the answers to these questions, and let's first of all apply impulse momentum equation to this problem. So apply the principle here, and let's see what we'll have. So this is the MP, that means the mass of the package, times V1, the velocity with which it is thrown. So it is thrown with a velocity of 3 meters per second. Okay, at an angle of 30 degrees. So, and once this happen, plus what will be is it having any forces? Once it has hit it, is it having any forces? No forces it is having. No impulse forces in the problem is mentioned. So is equal to mv2. Now this cart has this mass also and this mass also. Okay, so overall sum of these two masses times the new velocity v2, which we need to find it out. So if you put the values in this x component and y component, component wise we will be calling these equations. So the x component is mp v1 cos 30 degree plus no impulse force, okay, equals to this equation. So through this you can find it out v2. V2 is obtained component. After that, the another equation says that the next part was impulse exerted by the cart on the package. So impulse exerted by the cart, this is the cart to the package. So it is asking for the reverse reaction. So let's assume that um, this cart, this package actually has a component of fx delta t and fy delta t, and these are the two components here due to the reaction of the cart, due to the reaction offered by the cart. Once this package is dropped at momentum of mv1, the cart will be offering the impulse. So fx delta t is this component, fy delta t is this component. We are assuming it, and after the assumption we will calculate it and we will obtain what will be these impulse forces. We do not know the impulse forces till now. Is equal to mpv2. Remember that here we are only modeling this package, not the cart. That's why there is no mass of the cart. Okay, this is applied, or this is only modeling of the package, how the reaction will happen on the package. So the impulse momentum equation is written, and let's write it down. Its x component and its y component to obtain the fx and fy. So this component is written mpv1 cos 30 degree. This component x plus mpv2. Okay, we have written this and the force is obtained. So this was the fx delta t. Remember that the impulse force is not fx. Impulse force is fx delta t. Impulse force is fx delta t. Fx is only a simple force. When it is multiplied with time, it becomes an impulse force. And in the y direction, so mpv1 sine 30, this component, plus fy delta t, this vertical component, no other component in this direction, 0, obtained or solve for fy delta t in this way. So you can write down in the vector form, and the vector form, the impulse equation will be 18.56 I and 15 J. And in terms of magnitude, square of this, find it out, 23.9 Newton seconds is the impulsive force. So there was another thing that was there, which was the fraction of initial energy lost in the impact. So this is the amount of energy lost. So energy is always in terms of the movement. The movement happened in the in initial position, one position, and the another position. So let's take out the difference of the kinetic energies. So the difference in the kinetic energies will give us the uh, change in the energy. So that is actually the change or the lost is being calculated from there. So T1 is the initial kinetic energy, half mv square. This is 45, and T2 is the second kinetic energy. That includes both the masses. So it comes out to be, so in terms of percentage only. So this was the 45 joules was the initial energy, and this has actually reduced to 9.68 joules. So how much is the reduction? The reduction is about 78%. About 78%. Okay. So this is how you actually solve these types of problems, and I hope this is interesting. This is only um, uh, one form of way, or one way by which, one energy method by which you can solve the dynamics problem. You can apply certain principles to this. Okay, one conceptual question came here. Car A and B crashes into one another. Looking only at the impact, which of the following statements are true? So this is car A and this is B. So this is crashing in this. Okay, with a velocity of v1. It has a velocity of vb, and after this the overall velocity is v. Okay, so the total mechanical energy in the impact is same before and after the impact. Total energy remains same. Total mechanical energy remains same before and after the impact. This is not right. I don't think so. The before and after the impact, how can be it will be okay? I don't think so. Yes, the total mechanical energy cannot be same. The kinetic energy before and kinetic energy afterwards will not be same. That will not be same. The another problem, another part says if car A weighs twice as much as car B, car A is twice 2m, 2mb. That means it has. This is a truck. This is a simple. This is a simple nano car, something like that. It has a very high mass. Since car A weighs twice as much as car B, the force exerted on car B is bigger than force exerted on car A. This will not be the case, I don't think so, because the overall, this is actually the momentum transfer will be there. Car A weighs twice as much as car B. The force A exerted on car B is bigger than the force B exerted. No, because this is not, it cannot be bigger because from Newton's third law of motion, to every action there is an equal, underline equal. To every action there is an equal. So the reaction will be equal. Equal and opposite. Okay, it cannot be bigger. So I think it will be false. False it is. The total linear momentum is same immediately before and after the impact. Yes, because mv1 and mv2 will be, the overall momentum will be same. So I hope this actually helps up to solve most of your dynamics problem, this energy methods. So we have discussed Newton's second law of motion, how to solve the problems using Newton's second law of motion, how to solve problems using velocity displacement, can be solved using work energy principle, like we have used potential energy and kinetic energies, and we have also seen how to solve velocity time problems using impulse momentum equation. So I hope this video would be informative to you, and if you have any queries, doubts, please post in the Google Classroom, and we will try to figure it out, any problems that is arising due to this. Thank you for your time.